Hello, how are you today? Okay, well, welcome. Uh, so this week we were supposed to have two meetings. We only had one. We had the DevoWorm meeting, and that went pretty well. And then we were going to have our cybernetics meeting, but we canceled for this week again, scheduling conflicts. So that's where we're at. Let me start with a few items here. So the first thing I'd like to point out is, I think I did this about 2 weeks ago. This is a post. This is from the Lab Medium. This is a post on DevoWorm's video archive. So DevoWorm has been active for over 10 years now, but we have a video archive that goes back to the beginning of 2020. That's when we really started recording the meetings and putting them out into production like that. So we have, 4 years of archives at least. We also have the videos from the DevoWorm AI study group in 2019, so it kind of goes back a little bit further. But largely, before that, we were just recording special lectures and things like that. But now we record the whole meeting, for better or for worse, I guess. But the sort of the upshot of that is that we have a lot of archives, and we can transcribe these videos, and we can dive deeper into some of the topics that we've covered. So I've been creating transcripts for these videos, so we have that information as well, and I'm going to try to analyze that archive of transcripts. At some point, maybe we'll write a paper on it and see what we have in terms of our different topics. It's a very exciting format, I think. We have people who are welcome to present on their own research. We cover a lot of cutting edge papers. We maybe do some technical demos, things like that. So it's always, always good stuff. So just seeing what we cover over time would be very interesting, because it's kind of hard to keep track of all that. The other thing is, of course, we have a lot of tie-ins between DevoWorm and something I'm calling computational developmental systems. So I'm kind of including the stuff we're doing at DevoWorm, some of the stuff we're doing with computational psychiatry, and some of the stuff on critical periods as well. So, we have a lot of things that we haven't really kind of, kickstarted, that hasn't been active, and I'd like to see that happen under this banner. A lot of things that we do in DevoWorm that are sort of natural tie-ins to what we're doing in this group, or in the context of the computational agents, or things like cognitive science or neuroscience or whatever. And so I wanted to sort of kickstart some of those connections more explicitly. So DevoWorm started outside of our organization here, and it hasn't really been fully integrated into the organization. So I've been trying to do that for several years, actually, trying to get people to sort of pick up those connections, as well as myself. We've been doing some of that, but not as much as we could. So I'd like to sort of foster that. So this post is just kind of an introduction for people who are not familiar with the DevoWorm meetings to interact with our video library. And this is on the DevoWorm YouTube channel. So this is a separate YouTube channel just for DevoWorm, and it has all the meetings, and it has other content on that channel too. So we have small tutorials that I've done. We've had tutorials that Google Summer of Code students have done, and things like that. Okay, so the next thing I want to talk about is, this is something I think Morgan posted in the Slack. This is a Robert Rosen repository. I guess it's as a state. This reminds me of the thing that they did with W.R. Ashby's work, where the estate created this. It's a website. I don't exactly know what the address is, but they created an archive of Ashby's notes. Ashby's well known for have taken a lot of notes. Well, had a lot of like working papers and things like that. So they were able to publish that, after his death. And I think the same is true for Robert Rosen. So Robert Rosen, of course, was, he did a lot of theoretical biology. He did a lot of things with system science, physics. So it's really interesting work. And of course, he's well known for his work on relational systems and relational biology. So this is the repository. Let's see. Let's explore the collection a little bit. So this is just kind of set up so you can search 233 papers, I guess. And it goes from 1950 to 1998, so pretty long career. So this is kind of talking about some of his. So he's done work on structural stability. He did work on bifurcation diagrams and complexity theory, surface modulating assemblies, field theory and thermodynamics, a lot of stuff in applied math, and then relational biologies. That was one of his big areas. Some early computational work. So this is really interesting. Category theory, even, I think. So yeah, this is, and I think he was at the University at Buffalo in New York, or I guess also the University of Chicago. So that's where he was in the world. And then, of course, he was engaged in all these different types of research. We talked about relational biology in the cybernetics group. We've talked about it in the DeepSeek group. I don't know if we've ever really kind of gone through something like a book. That might be interesting because just getting like some perspective on that work might be very interesting, especially. I think we talked once about MR systems. It was like in a cybernetics meeting. So there's a lot of interesting stuff here, both in the cybernetics area, also in the theoretical biology area. It might be worth going through this and seeing what's, because I'd never seen all his work in one place before. Okay, so yeah, this is great. He lived from 1934 to 1998, and there he is as a child. Got his PhD in relational biology at the University of Chicago. I'm assuming that was kind of his own degree. Nicholas Reshevsky was his advisor. This is another person who's interesting. Nicholas Reshevsky. He did a lot of early stuff on theoretical biology too, and so it might be interesting to look at like what was going on there. Theoretical biology, biophysics, sort of that interface. And so yeah, that's kind of the idea. And again, this is stuff that we kind of cover in DevoWorm, kind of cover in our cybernetics group. Yeah, so they actually at SUNY Buffalo, they called it at the time SUNY Buffalo. It's University at Buffalo. They had a Center for Theoretical Biology. I guess I don't know if it still exists, but that's kind of, you don't see that very often, so that's an interesting point here. And then he moved on to Santa Barbara, or this institute in Santa Barbara, the Study for Democratic Institutions, where he began to develop the foundations of anticipatory systems theory. So this is the thing that we've been kind of focused on in terms of his work in the lab, and kind of thought about this anticipatory aspect of organisms and biological systems. So this is, again, a lot of things having to do with the good regulator theorem, having to do with, the predictive nature of, models within a biological system, being able to control your own behavior and anticipate environmental change. So it's really, really cool. So thank you, Morgan, for posting that. Okay. So then I also want to talk about this workshop. So this is, I guess, from this year's Neurops. And this was a workshop. It was Zador, Bengio, and some other people, Adil Razi, some other people in the field. And this is Neuro AI, fusing neuroscience and AI for intelligent solutions. So this is kind of like a Neuro AI. It's basically, it has some good Neuro AI stuff in here. So the abstract of this workshop, examining the fusion of neuroscience and AI. This workshop aims to unlock brain-inspired algorithms while advancing both biological and artificial intelligence. So their focus is on algorithms and different types of intelligence, and kind of fusing neuroscience and AI. So let's see. So there are some videos here. This looks like this is the whole session unlocked. So this is 8 hours of. You can see the video over on the side here. Different talks, and kind of going through some reinforcement learning, the causal cone, waves in the cortex, different types of topological spaces for looking at neural activity, equivariance expressed in capsules in space. So some good topics in computer science and graph neural networks, waves as memory, how to build abstractions, which is interesting. And this is in the context of the brain, not necessarily in computer science. So you have this kind of discussion of feature binding, Kuramoto oscillators, competitive learning, different types of learning, and then information bottlenecks and renormalization. So different tools from computer science and physics, different tools from complexity theory and applied math, and then different views of learning, where you can, you have to have sort of a policy for the system to learn. This one here, adversarial robustness and calibration. So different approaches to systems. This looks like a panel discussion with Carl Friston, Yashua Bengio, and Adil Razi. Kind of going through, I guess, some of the topics here. A definition of Neuro AI. And there was a Q&A, which, you can probably check that out on your own. So that's interesting stuff. So I'm not going to go through all of these talks, but, let's talk a little bit, maybe look at the posters and see what people were doing here. So you have all sorts of different interesting topics here. Here's one, need is all you need. Homeostatic neural networks adapt to concept shift. Dyadic learning and recurrent and feed-forward models. This one here, brain in the dark, design principles for neuromimetic inference under the free energy principle. So some free energy stuff. This is a population transformer, learning population level representations of intracranial activity. That kind of sounds interesting. Multiple temporal credit assignment rules achieve comparable neural data similarity. The brain's bitter lesson. And of course, we know the bitter lesson from reinforcement learning and Rich Sutton. Scaling speech decoding with self-supervised learning. This one, neuroastrocyte associative memory. Here's one on hierarchical control, which we talked about hierarchical temporal control last time, and kind of how that sort of paradigm operates. This is hierarchical control of reaching movements via compositional gain modulation. This is homeostasis-aware direct spike encoding, RNN replay, leakage and under-dampened dynamics. This is one on prospective learning, learning for a dynamic future. Not so gritty, internal representations of recurrent neural networks, path integrating more than one agent. So this is on path integration, which is a form of spatial cognition. I'm glad to see that because I worked with a colleague on some path integration work a long time ago, and I got familiar with the field and seeing what that looked like. And it's very interesting because there's a field of spatial cognition which focuses on the hippocampus and spatial memory, and then there's path integration, which focuses sort of on a phylogenetic approach and, mechanisms that are not necessarily in the hippocampus. So this is kind of an interesting kind of approach. Yeah, so this is liquid capacitance networks. And I think that's about it. I think there's a lot of really interesting work going on, a lot of sort of technical work that's really innovative. It's nice to see. And so, yeah, I leave that to people to explore on their own. All right. So let's move on to this document. And this is something that I prepared, I think, at the end of last year. We've gone through it. Actually, this is something we prepared several years ago, but I prepared the 2025 version of this. So this is a list of potential submissions and their destination and their due dates. So, for example, this Google Summer of Code project descriptions entry, this has been taken care of. I sent off the descriptions this week to INCF, and they're going to publish them and see what kind of interest we have. The two projects for this year are the DevoGraph project, which is a follow-up on the work that we're doing on graph neural networks and other types of graphs last year. So we had two projects last year, and we were building infrastructure for that. And we're going to continue on with that. And then, of course, the open source sustainability stuff. So we're going to either continue down the road of reinforcement learning or continue down the road of integrating agent-based models and large language models. So those are our two projects that are published. Now, the internal deadline for that is January 15th. That's for INCF's organizational application. And then later on, we'll have the ability to kind of change the wording of things. And then, the application period opens in, I think, early, like mid-March or something like that, maybe early April. I think we have to make the selections by May 1st or something like that. But basically, that's our timeline. So if people are interested in working on a project, they can, I think I have them on our GitHub repository. So we have a GitHub repository for GSOC through the ORL group. And I did update this for 2025. So our projects are up on the GitHub repository, github.com, ORL group, GSOC, the GSOC repository. And we're going to follow up on DevoGraph and follow up on open source community sustainability. And so, we have some Medium posts if you're interested in following up on this work. I have the post, the introduction to the LLMs and open source sustainability, and then developing adaptive neural networks. These were from two of our students here. Pocky did the adaptive neural networks, and of course, Sarah did the large language models for open source sustainability. So if you want to know more, you can click on those links We also have a history and alumni page for our GSOC students. That should give you some idea of what we've done in the past. So we're a very credible sort of group to work with. Okay, so that's Google Summer of Code. This one here, the NICWIC submission, that has also been completed, at least the version that was submitted by Jesse. So I think he's submitting for another one of these smorgasbords where, he has a bunch of people talk on one or more topics. He's going to see if it works out. So I don't know what the scheduling will look like on that. But again, we'll be working on that further into the year as we go. We have two deadlines or maybe more deadlines coming up. So there's the deadline for MetaScience 2025. They have a virtual pre-conference that they host online because I think the main conference is in Australia. I'm not sure where it is this year, but there's a virtual pre-conference. And I'd like to target that for submission. I'm not sure what it's going to be yet. I posted an inquiry in Slack. I just want to see who was interested, and I had a few responses, but we haven't had any discussions about this. So this is something that's coming up pretty quickly. We have to have something in by February 7th. So I might try to write something up and see where it goes, if it gets accepted, whatever. And then the event is June 30th through July 2nd, so it's online. And it's metascience.info. So if you're interested in submitting something to that, you have to get an abstract in by the 7th. And I think it's for just a talk. I don't think there's a paper. So this is coming up pretty quickly. And then the SIPS, which is the Society for Improvement of Psychological Science, they have a virtual component as well. You have to submit your abstract by February 14th. And that event is May 21 through the 22nd. So that's going to be, and I think what they're looking for there is like a workshop. So I'm not sure if that's something we want to do. That's going to be a little bit more involved in the meta-science submission. And it might be like two aspects of the same submission. I'm not really sure. I got to figure this out pretty quickly, I guess. So I don't know if it'll happen, but we'll see. And then there's this embodied intelligence workshop, of course, which happens every year. This one will be on March 1st. The deadline for this will be March 1st. So I have some things that will be submitted on that front. Basically I have to figure out which thing that we're working on will be good for this. I'll write up an abstract for it and put it in. And so that the deadline for that is March 1st. The event date is April 2nd through 4th, and that's also online. So, with embodied intelligence, if you register, you can submit one abstract. So if you're interested in submitting an abstract, please do so. And just make sure that you show up and present, because we've had some issues with that in the past where people can't make the time. We haven't, we've had like presentations that were kind of recorded and then forgotten about. So it's like, it's usually good to when you put in an abstract to attend the actual meeting. But anyways, we've been working on this very rich vein of developmental neurosimulation for several years now, and going to this conference and presenting on it and putting out papers related to that work. So it's really been a valuable experience. So we'll try to continue with that in 2025 and see where that goes. Yeah, actually, I think I should put out a blog post on that stuff, because I don't think we've gotten the sort of the benefit of like looking back on it, seeing where we've been. All right, so I'd also like to highlight Hussain's work on, he was at MIT Reality Hack. We talked about that last week. So he was very excited about his project, so let's look at it. So this is I think the headset that they're working on here. This is a screenshot, so it's not going to show the video, but I think it's just showing this. This is I guess it's an EEG headset over Quest 3. It's like the Quest 3 is here. Then you have this headset sort of skeleton, and it's kind of sitting over the top. So this is what they call OpenGalea. And this is a post from Reality Hack Incorporated, who's organizing MIT Reality Hack. So this is Team OpenGalea, and this is a summary of the project. This is something he posted in the Slack. This is Hussain Ather, something he posted in the Slack. So it says, we made this cool custom fully open source multimodal headset inspired by OpenBCI's Galea, but built from the ground up. We wanted to merge real-time brainwave sensing with immersive AR/VR experiences for a new level of brain-computer interaction. With EEG, EMG, and advanced machine learning models, our project aimed to decode neural activity and translate it into meaningful interactions in AR/VR. So, of course, EEG is the brainwave activity, EMG is the muscle activity. And a lot of times people will record EMG to either get some, corresponds with some muscle that's involved in some specific movement, or they'll use it to cancel out muscle artifact from the EEG. So there's a value to getting those multiple measurements. The core concept here is you have real-time interaction using EEG data with the ability to detect and adapt to user states like relaxation and focus. That's the core concept. So you're really trying to detect different user mental states. So sometimes if you can identify those states or the EEG correlate of those states, then you can sort of, incorporate that into the content. Or you can use that as an interaction, mode of interaction. So you can use that as a way to sort of cue in on things in the environment, or, use that as like sort of a way to select from a menu or something like that. The features here are hardware prototype, the headset, combined with a Unity-based AR/VR set of interactions. So it's this interface and then the headset and then the recording electrodes that you could see there was a framework for them on top. You can add pop culture inspiration, drawing on ideas from Pacific Rim, X-Men, Cerebro, and even elements of Neon Genesis Evangelion. We imagined a future where neuroadaptive AR/VR could enable incredible human-machine collaboration. So they had a nice process here over 3 days. So we talked about this last week, that they have like this introductory session and then they work on a project for a couple days and in different teams. So in day one, they finalized the idea for OpenGalea, drawing inspiration from OpenBCI tools, but building our own unique design. They began 3D printing the headset components using Ultra Cortex inspired designs, balancing functionality with aesthetics. Then they set up the Unity environment and integrated EEG signal processing frameworks. Day two then focused on machine learning, training models like EEG-NET and Inception Time on the PhysioNet EEG motor imagery dataset to decode focus and relaxation states. So you have to have some sort of benchmark for this, as they were trying to work on here. Implemented multiplayer AR/VR interaction in Unity, where real-time brainwave states influenced environmental effects, like flowers blooming or the growth of a virtual garden. We encountered some challenges with environmental variables, TensorFlow GPU issues, and data processing, but tackled them with persistence and quick thinking. So they had to improvise in some of their activities. And of course, there are a lot of challenges in this, because you have a lot of moving parts. You have the machine learning algorithms, you have the recordings, you have the sort of the interface and the content realm of the headset. So it's all stuff that's, even like if you were to do this on a desktop or a phone, you would have maybe a little bit better characterized computational environment. So all these things are challenges because, I don't think there are too many standards floating around for integrating these. Day 3, assembled the final hardware prototype and completed our VR AR demonstration. So they did a demo, made a demo, captured and edited a project video using OBS and Movavi, showcasing both the technical details and immersive experience of OpenGalea. Basically, they made a video of this. Submitted our project along with thorough documentation, code repositories, and an engaging narrative. So they were able to achieve an accuracy of 86 to 88%. They overcame their technical roadblocks and developed a fully open source platform. And so what they learned, collaboration is key, resilience pays off, respect the competition. So there were a number of different related projects, and then celebrate progress. Okay, yeah, so this is great. Thank you, Hussain, for that detailed summary of what happened at your hackathon at MIT. And it looks like you learned a lot of things along the way. All right, now I'd like to go back to our Slack channels, but instead of going through single channels and going back to maybe 3 months in time, I'd like to highlight some things that have been posted recently in Slack, things that I found, interesting, but really things from last week. So this first one here, we talked about the Rosen's relational biology and a lot of his work on anticipatory systems. And this is from Complexity Digest, which is a weekly mailing list where they put together links to different resources in complexity science. It's actually hosted from the UNAM in Mexico City, and it's Carlos Gershensen's group that puts this out. So this is actually, I think, an event they're hosting at their institution. So this is the International Conference on Anticipatory Systems and Rosenian Complexity, which I guess is reference to Rosen's work. This is going to be on May 22nd and 23rd of 2025. This will be at UNAM in Mexico City. So the call reads, the National Autonomous University of Mexico, or UNAM, by its research group on philosophy of computing, is proud to invite you to participate in the International Conference on Anticipatory Systems and Rosenian Complexity. So, inaugurated by Dr. Robert Rosen, anticipatory systems theory deals with how systems with the ability to anticipate, model, and act on future states. This conference aims to address anticipation in its many forms, including its philosophical, biological, cognitive, and technological dimensions. This year, 2025, will also mark the 40th anniversary of the original publication of Rosen's Anticipatory Systems, Philosophical, Mathematical, and Methodological Foundations. So this is, I guess this was published in 1985. This is the book on anticipatory systems. I think we may have kind of at least gone through this superficially at some point, I think in DevoWorm, but we haven't, like I said, we haven't done a chapter by chapter sort of review of anything by Rosen. That's something maybe we should target for this year since it's the 40th anniversary of the book, so I don't know. This conference is focused on Robert Rosen's ideary and notions of life, complexity, modeling, and mind. More at anticipation.philcomp.org. And if we go to the website, we'll see that this is the call for involvement. Actually, there was an international conference organized by Dr. Roberto Pulli in 2015. This is the 30th anniversary. We welcome contributions in, but not limited to, the following areas: philosophy of science, cognitive science, theoretical biology, foundational mathematics of relational biology, complex systems, medicine, artificial intelligence, and climate crisis. And kind of thinking about the anticipatory systems theory in all those domains. It's worth thinking about the, what's going on there and how, we might synergize with what's, if we kind of think about the topics, it might guide us in our explorations of the work. And then the welcome message from Judith Rosen. People often ask me what aspects of my father, Robert Rosen's scientific work, I think are most important. In one sense, it's a tough question to answer, because each aspect is connected to every other. So this is basically some of the topics here. Robert Rosen's work connected to this topic of complexity versus simplicity. So when you disassemble a system, how does that relate to the complexity of the system? So this is kind of related to sort of reductionism and complexity. 2, life is not caused by the components, but by the system organization. So there are no building blocks of life. The causal foundation for life is the same as complexity, system organization. 3, the type of complex system organization that causes life was one that incorporates the entailment embodied in my father's modeling rotation diagram in an active form. So there was this modeling relation diagram, not modeling rotation diagram. So this is where he did modeling of relational systems. And that's, if you've ever seen the diagrams in a couple of his papers, he developed a diagramming system for this. For the type of system organization that generates an anticipatory system, and the model-based, model-guided navigation and control strategies that characterize all life is what I refer to as somatic anticipation. So this is, again, the anticipatory model where, the idea is that there's some anticipation at different scales, not just like cognitive, but organismal, cellular, so forth. And so one of the things he focuses on is sort of the self and the relation between the self and some of these systems. So that's, leads up to this MR type system, which is, the notation is M, R, where M stands for metabolism and R stands for repair. So this is a metabolism repair system where those two functions are coupled. And I've seen people do variations of this where they do other types of coupled systems. And I don't remember, I think we reviewed this whole sort of systems approach in a DevaWorm meeting, and I can't remember which DevaWorm meeting it was, but I know that we discussed at least some of this. So yeah, this is something we'll come back to, I think. The next paper, and I think a lot of these are posted by Morgan, so thank you, Morgan, for posting these. This is a Distill article. So Distill was, and I don't think they publish online anymore, but they used to publish these really nice interactive articles on machine learning. And this article is from 2021, so this is the Distill article on a general introduction to graph neural networks. So neural networks have been adapted to leverage the structure and properties of graphs. We explore the components needed for building graph neural networks and motivate the design choices behind them. So this is the interactive form of this article. So these are the diagrams here where it's showing you go from layer 0, it projects, and this is a single node in a graph at layer 0. It projects to 2 nodes in layer 1, so this projects to this node here and this node here. Actually, every time you hover over it, it projects to different neurons, but so let's see. Okay, yeah, now it's projecting to different neurons. So you can see every node in layer 0 is projecting to corresponding nodes in layer 1, then corresponding nodes in layer 2, then corresponding nodes in layer 3. You can see that if I hover over layer 2, it shows the corresponding nodes in layer 3, and so on and so forth. So you see the way it's structured here, you have the different, you have the network in the different layers. Those nodes project to other nodes in other layers. And from that, you get this structure that has both sort of layered depth and then, this topology of the static network changes as you go from layer to layer. So there's another article, Understanding Convolutions on Graphs, that you might also check out. This is kind of convolutional neural networks, but in a graph theoretic approach, from a graph theoretic perspective. So they talk about graphs and how you can build graphs from all sorts of things that are naturally connected. So, you don't want to apply graph theory to everything, but there are a lot of things in the world that you can represent as graphs. You can understand the interactions between them, model those interactions as edges between nodes. So the set of objects and the connections between them are naturally expressed as a graph. Researchers have developed neural networks that operate on graph data for over a decade. Recent developments have increased their capabilities and expressive power, and we're starting to see real-world applications. So in this article, they divide their kind of review of modern graph neural networks into 4 parts. The first is looking at what kind of data is most naturally phrased as a graph. Second is to explore what makes a graph different from other types of data. Then third, we build a modern graph neural network, walking through each of the parts of the model, starting with historic modeling innovations in the field, moving from a bare bones implementation to a state-of-the-art GNN model. And then fourth, we provide a GNN playground where you can play around with a real-world task and data set. So this helps us build a stronger intuition about what those representations do for us. So this is their sort of interactive form of showing what a graph looks like. You have vertices, which are these nodes. That's the technical term. Edges, which are the connections between nodes. And then the global aspect of the graph, which is the number of nodes or the longest path. Basically, graph statistics that you can calculate on these structures once they're fully formed. And so you get a distribution of these different of VEU. So you get this triplet VEU, and you can represent each of those parameters with like a statistical distribution. And that describes the graph. That describes the structure of the graph and the nature of the graph. So you're taking data from the real world, you're representing it as a graph, you're building this triplet, and then you're visualizing it, then you're getting the statistics, and you can say something about the graph. Now you can make the edges directional or undirectional, and so that makes a difference in how your graph statistics look like. Not every data set or everything in the world is a graph. Obviously, there are things that aren't graphs. But you can use graphs to interpret a lot of things where you have a strong degree of interactivity. You can actually use this to represent images, and this is where they decompose an image with different properties, and they use like pixels in an image as the nodes, and then the relationships between the pixels as an edge. So this is where you have two pixels that are sort of diagonally connected. Actually, you have pixels that are fully connected with their neighbors. So it's kind of like a cellular automata type thing where you have a neighborhood, and that neighborhood are connected nodes. Then you look at their adjacency matrix. So that's the strength of connections, the strength of relation between any two pixels. And so you have this structure across the image, and you can see the adjacency matrix in the middle, and then the corresponding graph on the right when you take the adjacency matrix and you visualize it. So the adjacency matrix are these pairwise relationships, and then they map to some place in the graph. So you can see that you're just taking the image, the square image made of pixels. Each pixel is a node. The edges connect the nodes. And so this is the structure of the graph. It's basically just restating the image in terms of a connected model. And so you can actually do this with text. You can take like a sentence, break it up into tokens, and then plot the interactions between tokens. So the sentence graphs are all around us is represented in this matrix down here. This is an adjacency matrix. And so we don't think of sentences as being networks, but if you think about like if you were to sort of reorganize sentences into any combination of words in any order. So for example, if you have the sentence graphs are all around us, that sentence makes sense because we would put the words in that order and it makes sense to us. There's a syntax and a semantic value to that arrangement. But if we were to recombine the different words in their positions, so if we said all around graphs us are, that doesn't make any sense, at least to our ear. And so that's a possible set of connections between those words. And so we have this basically this sparse connectivity matrix based on a series of tokens in a sequential list, which is a sentence, and it's represented in this connectivity matrix. And we could also build a graph here where we just have this directional connectivity in one dimension. So this may be a little bit trivial in terms of the linguistics of it, but it's, well, not necessarily the linguistics, the computational linguistics, it's not trivial. But it gives us the structure then that we can play with. We can assign statistical values to it. We can understand the sentence better. So that's, and then we have this graph value data in the wild, so we can look at molecular structure. So this is where we have this 3D representation of a molecule, and we plot this, and we kind of figure out the structure. We plot this as an adjacency matrix, and then we can create a graph representation of this molecular structure. We can do the same thing for this caffeine molecule, different molecule, and it has a different adjacency matrix and a different graph topology. We can also build social networks, of course. This is the famous karate network. This is a scene from the play Othello, and it just shows like the structure of who's interacting in those scenes, and you can build a network from that. And so they kind of get at this idea of what types of problems that graph structured data. We have graph level tasks, which is where we take graphs as input, and then outputs are labels for each graph. So we basically try to take graphs once we visualize them and try to predict different topologies and what they mean. So, like if we saw a structure in nature, we might be able to predict that from the statistics. With graph neural networks, we're trying to do the same thing where we have a graph and have different graphs and compare them, and then try to sort of categorize those graphs. So we might say that, like, we might look at different motifs within the graph, like these rings. we might use that as a criterion for sorting these graphs and saying that can we find every graph topology with 2 rings in it. And so then we can actually, group those together as being like networks or graphs. And these 2 graphs are similar because they have a single ring. And so this is a lot like analyzing motifs in complex network theory, where you're trying to find different motifs and represent what those are. Okay, so, and then you have node level tasks, which are where we want to predict the identity of each node or the role of each node within a graph. So here we have a graph with unlabeled nodes, and then here we have a graph with node labels that we predict. So we're trying to, in this case, we're trying to predict what the 2 hubs are and the identities of those 2 hubs. So this is where you have a social network with 2 people, and those 2 people have a bunch of people who claim allegiance to them, so they're highly connected. And what you're trying to do is predict these hubs from the structure of the graph. So this is the Karate Club graph, where you have 2 hubs, Mr. High and John A. And so you can see that they're 2. We're predicting those locations from the data. And then the last prediction problem they present is edge prediction. So this is where they're taking images, and from the images they're extracting information about interactions between people in the scene and other objects in the scene. So you have, this is a scene from Karate Kid. This is where you have Daniel, Johnny, the referee is watching. These 2 are fighting. They're standing on a mat, and the audience is in the background. So you're representing all of these things in a graph. And so then you build this fully connected graph with unlabeled edges, and then the goal is to attach this sort of semantic information to the graph where you put labels on the edges. And so it describes a scene, it describes the relations between things, and we can use that as, a way to sort of build a model of interactions and maybe a model of prediction. So this is a nice article. It goes over a lot of these different concepts, and it has a lot of nice visualization aspects, a lot of connections between adjacency matrices and graph topologies, and showing how those are related. So I like the way that they do the interactive aspect of this. So this shows, again, how to represent graphs as data structures, showing the visualization and the relationship between the nodes, edges, adjacency list, and global aspects of this. So then they get into graph neural networks. They show kind of how this works, taking things from graphs, plugging them into these algorithms. And then, you're doing things like predicting nodes, predicting edges, predicting structure. So this is, a lot of technical aspects of graph neural networks, talking about how we can use message passing as a key part of understanding the dynamics of graphs, how information is passed from one node to another, and showing the distribution of information in that message passing protocol. So this shows aggregate information from adjacent nodes. This node here is taking in information or getting messages passed from these other nodes upstream. And so then you have this distribution of information, and you can actually use that. That's how one way in which graph neural networks are useful. Okay, and then they have this GNN playground. Here it is, where they have this, I guess this is a graph. It's doing model prediction. So if we kind of have to select our inputs here, we get a graph below on the left. And this, I guess we're looking at a molecule. And they have the legend down here. And then this graph, we're going to do some model prediction of pungency versus non-pungency. So the structure of the graph will predict the properties of the molecule. And then you'll have this graph on the right, which shows sort of the output of that. So let's see if I can run this. If I say size of 100, edge embedding of 20, node embedding of 25. I don't really know what these mean, but I'm just going to play with it. Let's try different aggregation functions. So you can see that it's changing, and the area under the curve is changing. The model AUC is changing. And the depth 4 layers, okay. So it's basically taking this graph topology. It has different properties, and it's going through this, basically going through the neural network, and it's analyzing the data, and it's producing this output. So we have this model of a depth of 4 layers, a mean aggregation function, and these parameters for the embedding, and then we get this output. So, this is something you can play with and get a sense of how this works. Okay, and then this shows just kind of a typical performance graph. This is how you report the data. So you have the number of parameters versus the test area under the curve for pungency. And then you're looking at sort of the performance metrics here. And this is what it looks like. So this is all, each of these, this is a model comparison where you're getting different points of different values. So we're just basically running the simulation again and again and then plotting out the results. Okay, so that's that paper. So this is really nice. Thank you, Morgan, for that. Okay, so this is another article, I think it was posted in one of the AI channels. I think it was developmental AI, developmental neuro AI, I think we call it. And so this is from the journal Device, which is a Cell Press journal. And this is called Magnetic Swarm Intelligence of Mass-Produced Programmable Micro-Robot Assemblies for Versatile Task Execution. So this is the graphical abstract where they're doing different things with these micro-robot swarms, such as lifting, transporting, and guiding. So this is where you have, in lifting, you have a high aspect ratio of the micro-robots. You can bend them around different dimensions. You have then high packing density of different, these micro-robots, where they're packed together along 2 dimensions. And then this high assembly stiffness, which is where you change the compliance of the micro-robots. And that can be used for guiding for goal-directed tasks. So I think it's interesting that you can do these kinds of different things and result in different behaviors and activities. So you have this collective behavior of these micro-robots doing different tasks, and you're doing things like modifying the physical parameters to get these desired results. So this is the name brief on the right here. Yang et al. Present micro-robot swarms that are mass-produced through the in situ replica molding and magnetization on a single microarray mold. By programming magnetization profiles of cuboid micro-robots can be organized into head to tail, elliptical facial, and face-to-face assemblies. Micro-robot swarms with distinct assembly features are deployed to perform self-climbing, self-throwing over an obstacle, self-lifting on an obstacle, cargo transportation, wire connection and disconnection, liquid metal shape modification, tube unclogging, and organism guiding. So these are different sort of tasks that they can do. So this is, I guess from these different types of assemblies, they can get to these endpoints. So all they're using are these physical constraints, and they're able to get these different behaviors. And so this diagram actually is from a post on DeepSeek. So this week people have been talking about DeepSeek and sort of how they're sort of a lot better than what OpenAI is doing. And so this is kind of showing the architecture of DeepSeek. This is an image that was posted in the Slack. And so it just kind of talks about the architecture, which has been sort of opaque to a lot of people. So hello, Morgan. How are you?
Good, thank you. Yeah, sorry for the delay here.
That's fine.
Yeah, I posted a number of kind of DeepSeek info papers, and the University of San Francisco Data Science Institute had a well, there was a couple of events this week that were LLM related, right? So the Buzz Robot had an event with the lead author on this PNAS paper that covered cognitive science of it was very much cognitive science of humans and LLMs.
Yeah.
So I don't know if you saw that. But,
I did not. Yeah, did you post that in the?
Yeah, it doesn't fit well into categories. So I forget where. I think it might have gone into data sci ML.
Okay.
Just because it seemed kind of LLM related.
Yeah.
I'm not sure that's I don't think LLMs and data science really have a lot to do with each other.
Right. Well, yeah. I don't know.
But yeah. I guess ML. Yeah. Interesting paper. It was very cog sci, or what the guy was presenting on was very cog sci, and this is one of those combined like I'm going to experiment with Mechanical Turk people and LLMs.
Oh, okay.
Right.
Yeah.
So and he made some points that I thought were he's putting up a thumbs. He made some points that were like also related to Wolfram spoke at Wolfram. Michael Levin spoke at the Wolfram Institute. I have not had coffee yet.
Yeah.
And one of the things, he was talking about his ideas on, cognition, or that I forget what the way he put himself, like a radical gradualist, I think is what he said. Right? That cognition is in a lot more places than you think, but the important thing was that if you don't test things, right, then you just won't know.
Right.
And he was making the extreme case where he was just like, well, do I know? He was talking about gene regulatory networks, and he was just like, you wouldn't expect that they were capable of all these kind of learning behaviors, but when tested, they demonstrate all these, the 6 forms of learning or something like that, right? And then he made the extreme case where he's just like, people then accuse me like of saying, does that mean that the weather is thinking? And and his point is, I'm not saying that. What I am saying is that you could test it.
Right.
if you had the tools on that kind of scale, you could test it and see, right? And this is leads into this PNAS paper. Well, it was PNAS Nexus. Just to be clear. But it was interesting. McClellan's on this paper.
Okay.
He's not the last author, but he's at the back there.
Yeah.
And but it's specifically covering reasoning in LLMs, right?
Yeah.
So giving people, like logic tasks, syllogisms, and then something more complicated.
Yeah.
And also, and then another dimension of varying content, the words you're using. So does the content kind of match your expectations, or does it contradict them? And then he had a third condition, which I didn't get to ask him about, which was kind of nonsense.
Right.
And I was wondering if so part of it was like, will you see something as true when it's like, dolphins or doctors or something like that, like I'm not doing this well on the fly, but I was wondering if they added the nonsense condition to match something. You see this in child development or cognitive development, right? That if you use nonsense words, kids will use them grammatically correct.
Okay.
Right, like if you're obviously using this thing as a noun, then you will do noun things to it, and if you're using it as a verb, then you'll do verb things to it. Right. And I didn't get to ask. I was gonna maybe try and follow up with him on that. But so they're testing humans, and they're testing like 4 or 5 different reasoning LLM models, right? And and certainly again, like to loop back to Levin's point, one of his things was that if you're not careful about your testing, if a model does something,
right,
you won't you shouldn't be dismissive of its reasoning abilities too quickly, and the humans are there because the reasoning, like even humans fall into these traps, if you will. So so it was interesting to cover it. This work had been done to, it got published like before the holidays, but it was done probably like a year plus ago, right? And so there was no DeepSeek in it.
Yeah, well.
But it was, then I thought what was interesting was to then look at, how LLMs are starting to be constructed for this particular kind of reasoning purpose, right?
Yeah.
And as well as like how that matches like cognitive architecture theory, as well as like cognitive sciences ideas about how we break problems down, into smaller parts, right? Which is again one of the techniques that some of these language models are or at least some of the designers are using as kind of goals, right?
Yeah.
I mean, goals for their training, and and of course, it all sort of comes back to something. I don't know if you remember me talking about deep algebra.
Right? Yeah, I think I remember that.
Right. So, and again, I forget the Pi Data Warsaw guy who coined this thing, but he was very much saying, well, like it was an extension of Karpathy's 2015 like kind of cursory work, but it was Karpathy's work where he was training on open math textbooks, I think.
Okay, yeah.
It's something like that, right? And I think this came out in some of this LLM training, or some of the reasoning model training is focused on math because it's this body of logic work, right? and where you've got structures built on structures, and so I've there's some, like, I don't know if you want, what you would call it, like there's some computer engineering to how they've made this more efficient model, and then there's some then there's some kind of training choices that they've made that I thought would be interesting to look at. But certainly, the I think the big take home is the efficient use, and again, like the efficiency of adding some reinforcement learning, some real directed reinforcement learning into the training. And then to add, so BuzzRobo, about that was Thursday. Friday was University of San Francisco, and University of San Francisco's Data Science Institute is an interesting group. The fast AI developers used to be professors there, and the data, they were really leveraging, the fact that they were here in San Francisco, right? And where to some degree you could say kind of data science was created by the tech industry. And so they had a guy from Modal, which is just it's a tech company, but it was very much, it was a great example of, a Berkeley CS, PhD who's grown up in this era where neural network optimization is a career. Right. It was a very young guy, but absolutely speaking as like a tech industry leader, right? And like talking, giving us a lot of really interesting insights in terms of, I guess what you'd call like MLOps of LLMs. And so interesting, of course, where this has become, they're doing things that we would have built PCs to do, right? I mean, I like totally built a 4 GPU workstation back at UCSF.
Yeah.
Like, what would that be, like 10 years ago or so now?
Yeah.
To run, of course, computational physics models,
Yeah.
right? And his company is showing you how to spin up, and he was saying, well, like, you can't game on these GPUs. You couldn't game on our GPUs either, right? Yeah. These were computation only, right?
Yeah.
But this emphasis these days that everybody's just running LLMs,
right?
and anyway, I'm glad I went because again, like I feel a slightly I feel I don't use them.
Right.
I don't use them at all. Right.
Yeah.
And I mean, I still feel somewhat good about that in terms of, like, I don't think that really needs to be your direction for artificial intelligence, but at the same time, they are, like they are the area. Certainly, the younger me would have definitely followed them because of the people and research focus and money that's gone into their development. Right. So that was definitely interesting. And again, he had some things to say about some practical things to say about working with these, especially on reasoning problems. Right. So it was, he wanted to separate out, just as the PNAS Nexus, like Stanford group, the models that were focused on reasoning.
Yeah.
And that if you're developing a chatbot for to basically deal with support stratification, or a bot to do email labeling, or these kind of things, it is like these reasoning models, total overkill. You don't need to be. And so I want to just sort of follow up from last week, in terms of the active inference textbook.
Oh yeah.
And I really want to have so I'm following Josh Bongard's course, which is nice, just in relation to the last paper you covered.
Yeah.
And so two more lectures this week that were focused on a basic neural network. I mean, I don't even want to call it basic neural network, like almost like basic logic truth table kind of stuff.
Right.
And then what was the but again, someone who tells you that his course is going to be coding.
Yeah.
like you're going to write more code for my course than anything that you've ever done.
Yeah.
Is like Josh Bongard talking about, just eyes wide open. He's got these pie bullet examples, and again, like he's definitely trying to give you an experience of building everything from the ground up. So very simple robot, like you wouldn't even call these robots, like they're very simple structures that he's going to apply kind of robot rules to,
right.
which is actually kind of nice if your end goal is biobots or something like that. Okay. Following up on the active, so again, not a lot of people came to that particular reading group, and the psychiatrist who's there is like not quite sure he's ready to code. but I'm following up with Active Inference Institute. Want more, it's like even Ryan Smith's step-by-step tutorial, like, you end up installing and using SPM, right? It's not exactly what I would call like a beginner, this is a far cry from Karpathy's LLMs from scratch.
Right. Yeah.
And so yeah, and it would be nice to have, like, because PyBullet is a part of this, thinking about some basic agent development in kind of following the world model papers that Saffron recommended for the RFP.
Yeah.
There was 2 or 3 papers from a particular group, and I'm blanking on them right now. I'll find them in a minute. Okay. But just thinking about how to get something that is a kind of easier code introduction, and I mean, it's not. So one, again, like I said this last week, but it's just awful to ask people to use MATLAB when it costs money.
Oh yeah.
And they give you ways to run. There's some way that you can run a compiled version of SPM, but then you don't get to really interact with the code in the same way.
Yeah,
anyway,
yeah.
It's they just shouldn't. or they should test they should test what they have with Octave so that people can run Octave. But the just thinking about the world models and inferences planning, it is is kind of the connection between the kind of active inference work and the reasoning behavior, or certainly breaking something down into kind of sequential sequence of operations, right? And that certainly in the particular papers, which I've got to find now so I can really weave them in properly here, but again, so much of the world models papers was really just about how far ahead can the model think or plan,
right?
And it's interesting, the reference in the textbook, the inferences planning goes back to this guy Adius in like 2002, and I'm super curious because that particular ML researcher, I don't know what you want to call him, actually worked with Sri Nagarajan here at the MEG Center.
Oh, really?
Like they had a paper. I don't know how Sri met him, but well, I think he was basically brought into San Francisco to be a data scientist. uh, uh, anyway, I noticed that he has kind of like the foundational paper, and it's probably not even a paper. It's like an abstract in a like 2002 probabilistic inference conference.
Oh yeah.
Anyway, sorry. Just again, linking together these things together with the active inference text, and hopefully some actual practical demos.
Yeah.
I distracted.
Oh, that's great stuff. Thank you. So yeah, as you were talking about live coding and how that's like there's like a standard of Karpathy's work, and then like that is a skill. I've tried doing that in teaching, and you have to kind of build that skill of live coding. I've done that in the group years ago. I used to do that more in the group meetings, but I don't as much anymore because it's very hard to do.
I mean, I think Karpathy plans it out.
Oh yeah, you have to plan it out. But I mean, just getting it to be like effective. Like what do I want to show people? I want to show people like me hitting buttons on the making mistakes, or am I demonstrating some thing that gives you a good visualization at the end? Or something works.
I've thought. Well, again, I haven't. I don't use LLMs. I've seen the kind of what is it, 3 blue, 1 brown. Is it 3 brown, 1 blue? Videos on transformers, but doing something like Karpathy's LLMs from scratch would actually be a great way to solidify some of these things. I just it's I don't know. I just don't know if I can do active inference without doing coding. If I'm gonna be able to understand it the way that I see Pard and Brian Smith and others talking about it.
Right.
Like it's super important. So trying to see whether it can use arXinfer as a replacement for kind of like the SPM stuff.
That's great. And then world models. You mentioned that, and it's just kind of interesting how I think we talked about world models last week in terms of how people have different kind of perspectives on it, and I think we're falling into the same trap we are with foundation models in some ways. Because that's like world models, what does that mean? Well, it's a representation of the world. Okay, what does that look like? It's like, okay, it's just anything that isn't like the trained, whatever the model's trained on. So I don't know, there might be something to like kind of thinking about world models as like, what are the cognitive science underpinnings of them?
Yeah.
Or what do you mean when you mean world model? Is it like, well, we talked about it a little bit in terms of Evergood regulator theorem, but like, what does it mean in terms of what are the properties of a world model? What would make an effective world model? Is it just a mapping from the world to like a mental representation? And I don't want to say mental in a machine, but like being able to recall something like a scene, or recall the basic structure of something, or maybe encoding it as a graph, and how much of that can you recover? Different things like that. I mean, really getting at like what it is, and
I thought it was a good example. This sorry, and I'll post this No, I posted the Nexus paper in the Slack. I just forget now under what
channel.
And yeah, so that second one down. No, down. Yeah. So the second to last.
Okay, this
one. Yeah, there. Yeah. That's a link to the paper. And
okay.
to your point, both of them made this so you got this kind of deep mind researchers thinking about the kind of theory, and then you've got this San Francisco tech guy who's thinking about how you use these reasoning models, and both are really emphasizing that your evaluation is everything.
Yeah.
Like how you're evaluating output from these models is really important, and like you said, like if you're not asking the right question, you're not going to necessarily understand the model's kind of depth, if you will, or the model's abilities.
Yeah.
And I liked this particular paper just in terms of you needed to be working with humans. You still needed to be doing cognitive science with humans.
Yeah.
I liked that. This wasn't one of these, it didn't have that feeling like it was psychologists being lazy about recruiting subjects and just testing an LLM with like, hey, we give these tests to humans, let's just do it to an LLM. Right. Or, like, hey, an LLM, has decent results on a theory of mind test. It must be conscious or something like that. Right? Yeah. So I would love to see more of these kinds of things, as well as how to like deep algebra was a focus because math is so important, right? Yeah. But I think so many of these one of Chris, I'm blanking on his name now. One of the modal guys that talked at the Data Science Institute, he was saying that like designing your evaluation, like no, don't just use an LLM to do your evaluation. and that that I think his point was that like a lot of people are using math because they know what the answers are. Right. And that's, I mean, it is, right? But these aren't people who care about math, right? So it gets to the point that they don't have a whole bunch of pre-tested logic problems or things like that for like how do you check that your system is doing all these things right. And so anyway, I felt like there was still a lot of hope in this era where again, this is the Data Science Institute at University of San Francisco, so in San Francisco, right? So you got this room of 100 plus students, who, when they got around to Q&A, a lot of them were asking like, am I still going to have a job? Yeah. And I kind of wanted to say, hey, look at this paper. You should all, maybe being a cognitive scientist would be a good idea. Yeah. It's funny how this is, it requires the skills. I don't know if you saw this, but on YouTube, there's this famous science communicator. He got famous because he went on Joe Rogan to argue with the ancient aliens guy.
Oh.
So he's an archaeologist. But he's talking this week because Cardiff is letting go half of its humanities staff. Yeah, and closing several schools, and I bet. I mean, you can also almost imagine that discussion of like, what are the degrees that are worth keeping, right? And if LLMs continue to be the dominant technology, then maybe they're going to need more humanities people to make sure that they're actually working.
Yeah. Why don't we go back to the paper? We have so language models like humans show content effects on reasoning tasks. James McClelland is in the author list. We had, all right, so the abstract reasoning is the key ability for an intelligent system. Large language models achieve above chance performance in abstract reasoning tasks, but exhibit many imperfections. However, human abstract reasoning is also imperfect. Human reasoning is affected by real-world knowledge and beliefs and show notable content effects. Humans reason more reliably when the semantic content of a problem supports the correct logical inferences. These content-entangled reasoning patterns are central to debates about the fundamental nature of human intelligence. So here we investigate whether language models whose prior expectations capture some aspect of human knowledge similarly mix content into their answers to logic problems. We explore this question across 3 logical reasoning tasks. So you have natural language inference, logical validity of syllogisms, and the Hussain selection task, which is a psychological test. We evaluate the state-of-the-art language models as well as humans to find that language models reflect many of the same qualitative human patterns on these tasks. Like humans, models answer more accurately when the semantic content of a task supports the logical inferences. These parallels are reflected in accuracy patterns and in some lower-level features like the relationship between language model confidence or possible answers and human response times. However, in some cases, the humans and models behave differently, particularly on the Hussain task, where humans perform much worse than large models and exhibit a distinct error pattern. Our findings have implications for understanding possible contributors to these human cognitive effects, as well as the factors that influence language model performance. So this is where they kind of talk about a lot of the different tests that they're doing, working from abstract reasoning tests. And let's see, this is what you were talking about, figure 1, where you have this sort of consistency, violations of consistency and nonsense, kind of going through that. They don't do any developmental evaluations, but that might be interesting, given what you were saying about, syllogisms and nonsense and development. And then this is the Hussain selection task, which is where participants are shown 4 cards. They're told that each card is a letter on one side and a number on the other. The participants are then told a rule such as if a card has a D on one side, then it has a 3 on the other side, so associating letters with numbers. The 4 cards respectively show D, F, 3, and 7. The participants are then asked which cards they need to flip over to check if the rule is true or false. So you're evaluating the rule as much as predicting the state of the flipped card. The correct answer is to flip over the cards showing D and 7. However, Hussain showed that while most participants correctly chose D, they were much more likely to choose 3 than 7. That is, the participants should check the contrapositive of the rule. not 3 implies not D, which is logically implied. But instead they confuse it with the converse. 3 implies D, which is not logically implied. So this is where you're looking at how, the intelligence, I guess, uses logical compositional rules to solve these problems and kind of come up with the best solution. So that's what they're talking about here. They kind of evaluate language models and showing the similarity across language models, the sort of the performance profile, and then looking at humans as well. So that's the article in PNAS Nexus. This is language models like humans show content effects on reasoning tasks. If we go to the data science ML channel, then I think Morgan has posted a number of things here that are, so we have some DeepSeek stuff. We have that paper. So why don't we go over kind of where we start with DeepSeek? So there's a lot of DeepSeek stuff this week. Actually, we can start up here with this. Yeah, go ahead.
Yeah, I was just going to say, so Charles Martin, just for, and my apologies for the LinkedIn links, but
okay.
Again, these are original posts by these people, so I have to link to something.
It's fine, yeah.
And it's such a minefield these days on what to link to. I'll find if they've got Threads or Blue Sky or something. But Charles Martin is the physicist, or he's coming from a theoretical physics background, doing field theory at University of Chicago. He's used that kind of background, especially in like renormalization group theory, to design Weight Watchers, and which you can find at weightwatchers.ai, which is a using condensed matter physics theory to look at your training weights, to analyze your training weights absent of data, right? And these are his breakdowns, or things that he's brought in that I think would be particularly interested given his particular focus. So he's very much a person who works in kind of advising corporations that want to apply this, right? Want to apply these technologies. However, he's coming from a very good theoretical background in terms of how he's especially looking at evaluating your training efficacy and or what's the right word? Whether you need to train more, or like he can find instabilities in your training weights that would suggest, that can tell you something about probable performance issues that you will have. Yeah. Just to give you a little background on that particular.
Yeah, I'm looking at this. Looks interesting. So that's this article here, Charles Martin, and talking about evaluating.
I'll put this in a thread. Again, I do really love his posts in terms of how he brings in good stuff to the discussion of training and weights. Ooh.
Yeah.
No, not that one. It is so hard to extract real links from these.
Yeah.
And then he's got some examples of these, but I think that's the main. I think we can get it through.
We've talked about Weight Watcher before in like the open source meetings. This is the kind of understanding your weight structure. And then this other paper, Implicit Self-Regularization in Deep Neural Networks. This is using renormalization, I guess, techniques to look at this. Yeah. And this is good stuff.
It's really good stuff, and I don't know if we've got, it would be interesting. He's got previous posts on things like, looking across, say, all the same deep learning models. I mean, all the same LLMs that say the Nexus paper's looking at, right? And saying something about their weight structure, and making predictions on issues that the various models might have on the basis of that. That's pretty interesting. And sorry, and then I dropped in a link to the just the one of the world models authors.
Which one is that? The last one here?
Yeah, so it's talked about in the so that's his paper, and then if you go to papers, you can see that, but you can also see just like the kind of world models, and the kind of videos. Is he doing with language?
Well, learning to model the world with language, mastering diverse domains through world models. So he's actually doing like stuff with world models. We're kind of thinking about the achieving discovering goals.
He's referenced in the he's referenced in the Adam Safran RFP.
Yeah.
And but that is interesting that like his 2024 ICML. I assume what he means by this is he's using LLMs. Maybe not. But again, the main thing I wanted to put him back in there for was just like you said, like what operationally, what does a world model really mean?
Right.
And
I think that's
I want to try and link it to this inferences planning.
That would be good.
And kind of not like we see it in all of these kind of game examples, which I think leads us in the wrong direction in terms of what the world model means.
So the game examples are kind of leading in the wrong direction.
That it's not. That we see this 3D world that the agent's operating in, and we think that that's the world. Whereas I think it's actually a more abstract, sequential learning, or sequential planning.
It's like it's not the actual kind of like one-to-one correspondence. It's actually this abstract tree or something.
But it is interesting though, right? In that if agents aren't put into this kind of world, right, that the sequential planning doesn't become a it sort of doesn't have any evolutionary value. Right. Again, like the Bongo course is taking over my brain space, but that's that is kind of Ryan Smith's point too in the step-by-step tutorial of active inference. Is you can't just active inference doesn't become active inference until you put an agent into a kind of rich environment.
Yeah.
I mean, a complex environment, and yeah. So they need to start. They need to start think. Like, to come back to the Rosen stuff. It's if there's nothing to anticipate,
yeah,
then you're not going to develop any of these things. But yeah, building up these kind of inference tables of, hey, if I see this, then this, or these other kinds of things that Bungard talks about early models being kind of tree tables.
Yeah. And then there's also the open-ended aspect. So having like the ability to kind of build new relations and things like that.
Yeah. And certainly this is the other part that that all the cool companies, all the cool ML companies now are talking about is continual learning and things like that.
Right.
Yeah. I just I've been looking around in terms of other who's doing you check out OpenAI's old spinning up in RL, right? Like they haven't updated their materials since 2017 or something like that, right? Went to Rich Sutton's Amy group. There's no there's course. They talk about like course material, and they are basically pointing you to you can do their Coursera,
right?
Which is cool, and maybe that's where they talk about something that's akin to, or like that would be on par with Bungard's evolutionary robotics. In terms of leading you and building something, but I haven't seen it. Anyway, I'm looking for that, right? Like, so many of the, models that I used to play with, from DeepMind, like, again, back when these companies were big on sharing.
Yeah.
I think they had this Quake 3 model that they used that I really liked, because of course I could remember playing Quake 3.
Yeah.
And I can't even get it to run because it's got like Python 2 dependencies.
Oh yeah.
I can install Python 2 on Fedora, but they've got this weird Google dependency on Bazel. And so you're kind of running it in a Java sandbox, and like Bazel 8 is like, no, I don't Python 2. Sorry.
Yeah. Yeah, it's definitely. So if we go back to the data science ML channel, we do have. If we go back up to, let's see, where did we want to start? I wanted to start here with this article from January 15th, or at least Morgan posted it there. This is talking about the top out large language models are saturating many common evaluations. So this is related to the thing that we were talking about earlier, where you have this problem. Go ahead.
Let me see if I can extract out. So this is Ben Blazek at Argonne.
Yeah.
Who is doing some really cool stuff. Again, because he has real world applications, and if you will, they care about actionable results, right?
Right.
So I'll drop this in the
channel.
I'll drop it in a thread
Okay.
on the yeah. So he's got that. So that's the paper SciCode.
Okay, SciCode.
Yeah. Which is cool. And oh.
What?
Oh shoot. No, sorry. I think I put this in the wrong thread.
Oh.
No, let me. Sorry. Oh, here we go. Sorry, I just added it to the. There you go.
Okay. This is the arXiv paper, SciCode, a research coding benchmark curated by scientists. Since language models now outperform average humans on many challenging tasks, it's become increasingly difficult to develop challenging, high quality, and realistic evaluations. And so this is where they're creating the scientist curated coding benchmark, SciCode. The problems in SciCode naturally factorize into multiple subproblems, each involving knowledge recall, reasoning, and code synthesis. So this is basically like a benchmark for comparing humans and language models, and so this is good.
I just wanted to add that this seems to. Sorry, go ahead.
No, go ahead. I was done.
So I also dropped the GitHub link.
Okay.
And
all right.
And just interesting off of that GitHub link, if you see the news there, so SciCode has been integrated with Inspect AI, and that's that next link.
All right.
And so this does seem to be an AI safety institute. I don't, it's one of those things where again, too many of the AI safety people that I'm introduced to are, like they're doomers, and their whole brain emulation will save us.
Yeah.
And I just have a problem with that. But if this is at least a good framework for improving, like testing multiple, it looks like some good things here in terms of here's how you would set up and run the eval for a few different model providers, and they've got OpenAI, Anthropic, Google, Grok, Mistral, Hugging Face.
Yeah,
that's kind of cool. So if OpenAI, if AI safety is going to do something for us, hopefully it will be doing things like that, giving us code infrastructure for improving model evaluation.
Yeah. So then we have the highlight of Sakana AI, which is this model. This is David Hough, who's involved in this. And this is just kind of a model, like where they have these self-adaptive models that modify their weights during inference. This is kind of world model stuff, kind of from the Hough and Schmidt-Huber wrote the 2018 paper on world models, so they're involved in that. But also David Hough is also involved in artificial life approaches. So interesting stuff there.
It's definitely let me also just put an added here's their actual blog post on on this.
Okay.
Um,
so kind of transformer squared. Okay.
Yeah.
These are self-adaptive large language models.
Yeah. And I, you know, apparently, well, this is interesting in that it brings up and contrasts itself with a number of other techniques like LoRa that are being widely used because everybody's dropped everything that they're doing and they're working on large language models, right? So that's kind of cool. I always like something that starts with like the core ability of this thing is achieved through the singular value decomposition. And it's just like, well, if it is, then anyway. I mean, again, this is why I love Gilbert string, and the SVD is the root of everything.
Right.
That's the root of everything. So it shouldn't surprise us. No. But it does make it sound like you're just doing PCA on something.
Right. Yeah.
Some internal variables.
I mean, this blog post, it reads kind of like it's biologically inspired, but it's really just kind of like,
it's not biological. Yeah. What's wrong with just saying it's algebraically inspired?
Well, that's not cool. I mean, that's
not cool.
Well, I mean, I think it's cool. I don't know, but it's. So I don't know. Let me.
But I'm like they're great. They still submit papers to A-Life and things like that. So
A-Life isn't all biologically inspired. It's got
right. True. And like if I learned anything from Gecko, it's how little evolutionary algorithms and modeling has to have any connection to biology.
Well, yeah. A lot of it's optimization and
yeah.
So let me go back to the channel. I just want to go over really quickly this stuff on DeepSeek, because I think that's really kind of the timely stuff here. So the Charles H. Martin post starts with DeepSeek was made by quants. And then there's this DeepSeek R1's recipe to replicate O1 in the future of reasoning LLMs. This is where, they have this performance chart, DeepSeek R1. So, they've been releasing models this week, DeepSeek, and they've been kind of being compared with the stuff that OpenAI is putting out. And so O1 being an OpenAI model. So they're, kind of comparing DeepSeek model performance here and showing what it can do. This is Charles H. Martin again on LinkedIn. For those longing for a DeepSeek deep dive, here's a very dense review where it kind of goes into some of this is distilled AI. This is just kind of an outline of this deep dive. It's a primer on DeepSeek R1, the architectural foundations, mixture of experts model, multi-head latent attention, FP8 quantization, multi-token prediction, then the training pipeline, where you have supervised fine-tuning and then reinforcement learning, group relative policy optimization or GRPO, and kind of going through that, plus comparison to other types of policy optimization models, which is something I'm not familiar with at all, but that might be an interesting thing to look into. Emergent reasoning behaviors, distillation reasoning in compact models, OpenR1, objectives of OpenR1 and impact on the community. So there's a lot of very heavy emphasis on reinforcement learning here.
Absolutely.
Wouldn't you say?
Absolutely, right?
Yeah.
And yeah, and I added a link to the the article itself.
Oh, this is the actual. Okay.
Yeah, just so you can drill down, and and wanted to just add that I think it's in call for involvement events. Yeah, second to last there is the deep multitask and meta learning course from Stanford.
Okay.
And yeah, you know, like you said, like this kind of interest that everybody has in DeepSeek.
Yeah.
It is just it's a reminder that there has been a lot of work that is useful to cover. I think you can relate it to the active inference, and you know, I like the fact that it comes back to a lot of the discussions that you will have in an active inference training agent kind of context.
Yeah.
And again, like I'm both looking for easy way. You know, these are things that Josh Bungard's going to talk about at some point.
Right.
Because, you know, certainly when you look at how people train robots,
yeah,
that these are these all of those things that you saw in that distill table are you know things that you will need to know, right? Especially, and I dropped this into Bratenberg vehicles, I think. I mean, so one is the third thing back is Mech Lab, which is Bongard's lab.
Right.
But for history on Ross and kind of just, you know, training, like they had a talk from a Willow Labs guy.
Okay. Yeah.
And you know, this is Jan LeCun's talking about, you know, I mean, I think it's interesting. I had Jeff Hinton and Jan LeCun saying stuff in my feed this week. Jeff Hinton saying that AI is already conscious and it's going to kill us. And Jan LeCun is saying that this is the decade of robotics.
Yeah, it's kind of a divergent view there.
Yeah. And I'm, you know, again, if I have to pick a side,
yeah.
And again, my side would still be the with kind of like the Ross Open Source Robotics Foundation.
Right. Yeah.
You know, I'll still go with robotics and you know how much we still have to do in terms of producing a robot that can pick up a slippery object, or you know, and things like that. Like, you know, how difficult sim to real transfer is still.
Yeah.
And I know it's getting late, but sorry, on that particular point, I was saving this to sim to real transfer. Nope, sorry, I forgot now.
Okay. Well, this Chris Reed, this is Chris R. Reed. And this is a lab web page where these researcher doing things with emergent behavior, complex systems.
He came up because of an Active Inference Institute talk from Matthew Sims.
Yeah.
That was covering slime molds and philosophy.
Oh, okay. That I saw that come up in the feed there.
Yeah. I thought it was interesting.
Yeah.
I thought it was interesting. I am still trying to think about what I was trying to say before. See, robotics. Anyway, you keep going.
Okay, so yeah, that was the Chris R. Reed website. He's doing a lot of things with collective behavior, with ant learning, ant optimization. We talked about swarm intelligence and ant swarm optimization. Slime molds, of course. Things on collective decision making, et cetera, et cetera. So that's something to check out. Then I'm going to go back to the where were we with the data science ML? Just finishing up with the stuff with DeepSeek and R10 and R1. Morgan posted more on he posted on the language model reasoning, so there are more posts on that.
Yeah, that was just the link to the event. Yeah, if anybody wanted to join the Zoom. Yeah.
And then a link to the ARC Prize, which is, of course, this where we have R10, or an analysis of DeepSeek's R10 and R1. R10 is more important than R1. And kind of this is where I got this diagram from that I showed to start things off. And this was the DeepSeek R1 architecture by Sarah Chan. This is kind of describing the architecture. And again, like this is beyond what we kind of talked a little bit more about it, but this is still kind of, I guess the whole point of this architecture is to say that it's shocked people how well it works compared to like some of the other models, and that it's open source and it doesn't take very much compute and all that. So this is kind of why we're interested in it, and getting this, figuring out the parts of this architecture that makes it tick. So this is kind of talking about some of the advantages of it and how how it kind of getting into the architecture and thinking about some of the shifts in the broader field of AI and large language models.
Yeah, and that was why it was nice to kind of cap off the week with this presentation from Modal, which was very much about kind of like the MLOps of LLMs.
Yeah,
and of course how much that has to do with money.
Yeah,
right. I mean, in terms of what are you spinning up, and what are your justifications for doing that? Because again, speaking to a room of data science students who are going to be, not really doing this for academic research, but for commercial interests, right?
Yeah.
And that's what's the pricing, and the what they're calling inference is when you're actually asking the model a question, right?
Yeah.
Excuse me, or having it make a prediction about the next token, and all about the economics of it.
Right.
So not tremendously interesting. I do think that there's I've seen some good market analysis of like what the hell's wrong with OpenAI, where they seem to be coming out with a new model every week before anybody's got to understand what the previous model that they released is doing. Anything like that. But I really like that distilled breakdown of kind of the main the topics, which it would be good to be familiar in terms of understanding how they achieved this, as well as like again, I feel like it's not active inference, because I don't think active inference is this philosopher's stone, but certainly so much of this stuff is about finding interesting areas in a really super high dimensional space, right?
Yeah.
And being able to reduce your to ignore a bunch of uninteresting areas in that.
Yeah.
And certainly, and then distillation, which seems like, again, like, I'm glad I don't have to write business cases for these LLM companies, but like, I don't see how you prevent a model from being distilled.
Right.
Like, I know you can say, like, please don't use this to distill a model that's going to be a competitor.
Right.
but at the same time, like, how, like, it just, I don't see how you watermark that.
Yeah.
And so, anyway, more importantly, the AI, to come back to kind of like the AI safety framework. Obviously, us researchers should be really interested in what we can gain from looking across all of these models, and being able to use them more adeptly like that, in terms of being able to get all their best bits.
Yeah.
And but I still, other than like Brain LLM, I haven't seen a good, I don't know. I mean, other than like the kind of CogSci that you saw in that PNAS Nexus, like I haven't seen where an LLM is helping us as researchers.
Yeah.
Like Brain LLM is a nice proposal in terms of, hey, what if you had this kind of research assistant that could tell you about the existing literature and suggest ideas,
right,
for like, but I think it's something that we haven't actually thought about. How would we, like, what would be important evaluations for us,
right,
as academic researchers? Anyway.
All right. Well, I think that's it for today. Thanks for the great conversation about these different things, and hopefully, we keep going. I think this line of kind of robotics and AI, I think you're on a good track here. So we'll see where that goes.
And what I want to bring in, to it is basically embryology. Well, and I love the fact that xenobots, it was a manipulation of embryonic cells, right? And removing them from that context, and so and as Josh Bongard says, the Czech reference that gave us the word robots was originally about biological robots. So we're the biological roboticists are the real roboticists.
Yeah. All right. Take care.
All right. Take care.
Let's see.